Hi there, organic chemistry students. This is Mr. Dion, and in this video, I'm going to tackle some of the questions from Chapter 4 in the ACS Organic Chemistry Study Guide, 2nd edition. So the topic of this chapter is acids and bases, and we're going to jump right into it here with practice question 1. So we're going to start here. Which compound is predominantly a Lewis base? Okay, so the first thing you're going to need to know here is the definition of a Lewis base and, of course, a Lewis acid as well. Okay, now a Lewis base, the quickest definition I can think of is an electron donor. Okay, and the way you can remember a Lewis acid is Lewis acid is an electron acceptor. All right, so a mnemonic that my students will use sometimes is they'll say acid, acceptor, so A and A, so 2 vowels, A and A, same letter, and then a base and a donor, so 2 consonants, if that helps. Now, if we take a look at each one of these, which one of these is going to be a Lewis base and an electron donor? Well, if we take a look at the first one, we can see that that's a carbocation, so there's no electrons to donate there. If we take a look at B, though, we see we have a carbanion, and therefore there's a lone pair that's not drawn in, but it's implied that there's a lone pair on this carbon with a negative charge. And so that could be an electron donor, right? It could serve as a nucleophile. C is just a straightforward alkane. It's just isobutane. There's no electron donation there. And then aluminum trichloride, D, it's actually one of the most classic Lewis acids, okay? I would actually recommend memorizing the AlCl3. AlCl3 is a Lewis acid. It's an electron acceptor, and the reason why is because aluminum has an empty 2p orbital, and so it can accept electrons. And so the answer is going to be B. We have a negative charge plunked right on that carbon of our carbanion, and so it's going to be a Lewis base. All right, question number 2. What is the role of the alcohol in this reaction? First thing you've got to be able to do is recognize an alcohol. And so this is our alcohol right here. Next, you've got to be able to recognize an acid base, conjugate acid. And so you can see that the alcohol is becoming an alkoxide, thus it's donating a proton, and therefore this must be our acid. You can see that the sodium amide here is going to be our base, which would make the alkoxide the conjugate base and the ammonia the conjugate acid. And so the role of the alcohol rather, is going to be an acid, okay? And so you need to know the Bronsted-Lowry definition of an acid. So an acid, Bronsted-Lowry definition is a proton donor, okay? Whereas a Bronsted-Lowry base is going to be a proton acceptor. Okay, question number 3. What's the conjugate base of phosphoric acid? Well, you need to have the names of acids memorized. You need to know what phosphoric acid is: sulfuric acid, hydrochloric acid, nitric acid, hydroiodic acid. I could keep going, but I'll stop there. And so as soon as you see phosphoric acid, you should be able to say phosphoric acid is H3PO4. And we're looking for the conjugate base. So the conjugate base is what's left over after it loses a proton. So if the phosphoric acid donates H+, so I put a minus sign here for losing H+, you're left over with H2PO4, and it's going to have a -1 charge. And so our answer is going to be C. Number 4, what are the Bronsted-Lowry bases in this equilibrium? So like I said previously, you need to be able to recognize an acid, a base, a conjugate acid, and a conjugate base. So going back to the idea of Bronsted-Lowry, remember a Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. And we can see here that the water is donating a proton, right? We have water and we have hydroxide, it's conjugate base. Therefore, the water is acting as the acid, which must mean that the phosphate ion is the base, right? And you can see the phosphate ion accepted a proton, okay? So that's our base, that's our acid. So we've got one of the bases labeled. Now, if you ever struggle to determine, which one of these is the conjugate acid and which one is the conjugate base, just look at the reaction in the reverse direction, okay? And you can see that the hydrogen phosphate, that's donating a proton. Therefore, that must be the conjugate acid, right? Because acids are proton donors. The hydroxide is the conjugate base because it's accepting a proton, right? It's gaining a proton when it becomes water in the reverse direction. And so our bases are going to be the phosphate and hydroxide. So our answer is D. Moving on to question number 5. Now I've covered Lewis acid, Lewis base definition. So a Lewis acid is an electron acceptor. A Lewis base is an electron donor. A Bronsted-Lowry acid, covered that as well. Bronsted-Lowry acid is a proton donor. Bronsted-Lowry base is a proton acceptor. Now, what you have to understand is that anything that is a Bronsted-Lowry acid or base is not necessarily going to be a Lewis acid or a Lewis base, but anything that's a Lewis acid or a Lewis base is going to be a Bronsted-Lowry acid or base. So if we're looking for which one of these is not a true statement, so we're looking for something that is false here, okay? All Bronsted-Lowry acids are Lewis acids. That's true. B, all Lewis acids contain hydrogen. That is definitely not true. Okay, if you remember, I told you one of the Lewis acids you should memorize is aluminum trichloride, right? It's an electron acceptor. It does not have hydrogen in it. C, all Bronsted-Lowry acids contain hydrogen. That's true because they're all proton donors. All Lewis acids are electron deficient. Well, a Lewis acid is an electron acceptor, so yes, it would be electron deficient. Okay, question number 6. I feel like I've gone over this quite a bit, so we won't spend too much time on it. How do we define a Lewis base? Well, the definition of a Lewis acid was an electron acceptor, and the definition of a Lewis base was an electron donor. And so we're going to just pick here electron pair donor. Okay, which one of these in number 7 is a Lewis acid but not a Bronsted-Lowry acid? So to review, a Lewis acid is going to be an electron acceptor, okay, but is not a Bronsted-Lowry acid, which is a proton donor. So we're looking for something that can accept electrons but will not donate a proton. And if you look at in A, we have aniline. Well, that has protons that could be donated. TSOH, if you don't know what TSOH is, you should. Okay, you should memorize this. This is tosic acid or toluene sulfonic acid, tosic acid, which is a strong acid. Okay, and so it certainly has a proton to donate. And I know you know the last one, which is sulfuric acid. Okay, so those are all Bronsted-Lowry acids, but aluminum trichloride is a Lewis acid. It has no protons to donate, but it is an electron acceptor for reasons that I already discussed earlier in this video. Same vein in question number 8. What is a carbon-based Lewis acid? So again, we're looking for a Lewis acid. We're looking for an electron acceptor. Well, let's see. We've got methane, we've got a carbanion, we've got a carbocation, and we have a radical. Well, which one of these is the most electron deficient and willing to accept electrons? Well, it's certainly the one that's positively charged because it can accept electrons to become neutral. Question number 9. In this reaction, which species acts as a nucleophile? So you need to understand nucleophile, electrophile. And so a nucleophile is a nucleus lover, so to speak. Now, what is the charge of a nucleus? Well, a nucleus is positive, isn't it? Positive, right? Because what's inside the nucleus? Protons, which are positive, and neutrons, which are neutral. And so we're looking for something that would be looking for a positive charge. Well, what's attracted to a positive charge? Well, based off of electrostatic force, it's going to be something with a negative charge. And so our ethoxide here is going to be our nucleophile. And you should be able to recognize that just by looking at this mechanism. You know, you should practice your mechanisms enough that you can recognize nucleophile. And then, of course, this would be our electrophile. Okay, question 10 asks us which one of these species is the most electrophilic? And so we said a nucleophile was a nucleus lover, and an electrophile is going to be an electron lover, okay, so to speak. So we're looking for something that is positive, that's seeking electrons. We've got water, hydronium, ammonia, and methanol. Well, hydronium is the only one that's positively charged, so it's going to be seeking electrons the most. Okay, what must be an electrophile? So an electron lover, okay, or something seeking, maybe I'll put seeking electrons. Seeking electrons. We've got Bronsted-Lowry acid, Bronsted-Lowry base, Lewis acid, Lewis base. Well, you remember that a Lewis acid is what? An electron acceptor. And so it's certainly acceptor, so it's certainly seeking electrons. Okay, now before I answer question 12, which one of these is the strongest acid? What I want to do is switch over to another page here because we're getting into the section here of this chapter where it's starting to ask us about pKa's and which proton is more acidic, which one is less acidic, and all that kind of stuff. And first of all, you should understand where pKa comes from, right? pKa is the negative log of a Ka, and you should know what a Ka is, the dissociation constant for an acid. So it's a negative logarithmic scale. And so the more negative your pKa is, the stronger your acid is because the more it's dissociated. And so we can very quickly look at these here. We've got propane, ethine, water, and benzoic acid. If you're looking for the strongest acid, you're looking for the lowest pKa. So low pKa, strong acid, high pKa, weak acid. And so very quickly, we can just say, well, the lowest number here is 4.2. So benzoic acid is the strongest acid. But as I was saying before, I want to skip ahead here. And I stuck this slide in here. This obviously isn't part of the ACS study guide, but I put it in here because students ask me all the time. They'll say, Mr. Dion, do you have any shortcuts or any tricks for mastering the content in the acids and bases section of organic chemistry? And I can give you that answer very quickly. And the answer is, if you want to, go from, getting maybe a B to an A in acid-base chemistry, all you have to do, my friend, is memorize pKa values. The more pKa values you memorize in organic chemistry, I'm going to use the E word, the easier organic chemistry will become, and the faster you can get through these and just get the right answers. So I implore you to try to memorize a few pKa values, okay? It will come in handy pretty much every day that you're studying organic chemistry. So just to recap, kind of what I was saying before, each pKa unit represents an order of magnitude. So if you have an acid that, say, has a pK of -7 and you're comparing it to an acid with a pK of -9, so the difference between -7 and -9 is 2. And so that would be 10 to the power of 2. And so an acid with a pK of -9 would be 100 times stronger than one with a pK of -7. And so I went over that example here. Let's say you have HBr and you're comparing it to HCl. Well, HBr has a pK of -9, so it's 10 times stronger than HCl, which has a pK of -8. And so this table comes from David Klein's textbook, and I don't know what textbook you're using to study organic chemistry at your school, but you can find pKa values all over the internet in any organic chemistry textbook. So let's just review these, and then we're going to go back to the questions. But you can see here, HBr, hydrobromic acid, is a very strong acid with a pK of -9. Then we have HCl, hydrochloric acid, very strong acid, pK of -8. Then we have sulfuric acid, right? This is H2SO4. Again, a very strong acid, has a pK of -3. Then we have hydronium, right? Hydronium, H3O plus, is actually considered to be a strong acid. In fact, anything that has a pKa of 0 or less than 0 is going to be considered to be a very strong acid. So that would be our strong acids. Now, is this an exhaustive list of strong acids? The answer is obviously not, but it's going to help guide us through the rest of this video. So then we have an anilinium ion. So if you don't know what this is called anilinium, right? This is aniline. So if you protonate it, you get anilinium, which is a pK of 4.6. You could even say it's close to 5. Just say it's close to 5. Same thing with this one here. You should be able to recognize this acid immediately. This is acetic acid, right? It's the acid found in vinegar. And you should know the pK of acetic acid is around 5. We have H2S. So if that's aqueous, that would be hydrosulfuric acid. It's got a pK of 7. And we're going to compare that to water in just a second, which isn't as strong an acid. Then we have a 1,3-dicarbonyl. So this one here, if you're wondering, like, what is this thing here? Sometimes we call it a diketone, but you see how the numbering here would go 1, 2, 3 like this. So we call it a 1,3-dicarbonyl, right? Because this is a carbonyl. Has a pKa of 9. Then we go to ammonium, right? You guys should all recognize ammonium, which is a pK of, again, around 9. I got a few more here before we go back to the questions. Then we have phenol. So this is phenol, okay? It's an aromatic ring with a hydroxyl. As long as you know it's 10, okay? 9.9 is the number that they put here, but 10 is fine. Then we have water, which is 14. And if you remember, the H2S was, that was 7. So you can see that H2S is a much stronger acid than water, H2O. And the reason why is because the conjugate base of H2S is so much more stable, because sulfur is a much bigger atom than oxygen, and it's better at stabilizing the negative charge than oxygen is. And then we have a couple of alcohols here. They put ethanol. So this is ethanol, and this is called tert butanol. They've got a pK of 16 and 18 respectively. And so as long as you know an alcohol is somewhere in the neighborhood of 17 is good enough. Then you have acetone. So this is acetone. Acetone is a ketone. And so acetone has a pK of 19. Then we go to an alkyne, a terminal alkyne. So if you have an sp hybridized carbon with a hydrogen on it, it's got a pK of 25. Then we have ammonia, right? NH3, which is a pK of 38. Then we have, this is ethylene, but if you have a bond between an sp2 hybridized carbon and hydrogen, it has a pK of 44. And then we have an alkane, which is the weakest of all. This is just ethane. So if we have a sp3 hybridized carbon hydrogen bond, we're going to say the pK of that proton is around 50. So you remember that the stronger the acid, the weaker the conjugate base, and the weaker the acid, the stronger the conjugate base. And so you can imagine this is an extremely strong base. So again, I strongly advise you to try to memorize these values moving forward. So let's go back to the questions in the ACS study guide. And now that we have that knowledge, it's going to enable us to answer question 13 pretty quickly. Which hydrogen is most likely to be abstracted when this molecule is reacted with sodium hydride? So sodium hydride, NaH, right? Hydride is a base, right? It's a base. So which one of these is the most acidic? Well, we can write down the pKa's, right? This carbon is sp2 hybridized. So we'll say the pKa here is around 44 or 45, whatever. For C, we have an sp hybridized carbon, so our pKa here is going to be around 25. Again, just ballpark, okay? Here, we have an sp3 hybridized carbon, and so those hydrogens on that methyl group, I would say, would be around 50. They're actually going to be less than 50 because it's attached to an oxygen, which is electron withdrawing, but we'll just put here 50. Okay, close enough, or even less than 50. And then here we have an alcohol, and so that's going to be somewhere, we'll just say 16 to 18 would be the pKa of that one. And so we can see that the alcohol is certainly the one that's going to get pulled off, right? It's the most acidic. It has the lowest pKa value. So you see how memorizing those, how fast you can answer those. Now, another thing you could do is in this particular case, and I don't want to spend too much time on this, but since carbon, nitrogen, oxygen, for example, since those three atoms are all in the same period, you can use electronegativity of the atoms and say, well, if you take a look at these three, right, all of these hydrogens are attached to carbon. Okay, so all of those hydrogens are attached to carbon, and oxygen is more electronegative, so it's going to be better at stabilizing the negative charge. But again, just memorizing the pK values is almost like a shortcut in a way. Okay, let's take a look at these. So next one, which proton would be most acidic? If we look at A, that's a phenol, right? If you look at this portion here, that's a phenol, and we said the pK of a phenol was around 10, so I'll just put around 10 here for that one. Okay, we have a carboxylic acid here, and we said the pK of acetic acid was around 5, so we'll just put 5 for this one here. This one's next to this carbonyl, so I'm going to say it's going to be close to 19-ish, something like that. And for this one here, this benzylic carbon here, I would say, it's going to be, if you were to deprotonate that, the negative charge is going to be stabilized by the aromatic ring. So I would just say less than 50, definitely less than 50, which it most certainly is. But either way, you can see that by far, the one that's part of the carboxylic acid is the most acidic. It has by far the lowest pKa. Question 15, rank these from the weakest to strongest acid. So if we take a look at each one of these, what do they all have in common? They all have a +1 charge, right? They all have a +1 charge. In the first two, the positive charge is on an oxygen, and in the second two, the positive charge is on a nitrogen. So if we just group these in terms of positive charges on oxygen versus positive charge on nitrogen, well, the ones that have the positive charge on the oxygen are going to be stronger acids because oxygen is more electronegative than nitrogen. Therefore, it's less able to stabilize that positive charge. And therefore, 3 and 4 are going to be the weaker of the acids. So right away, we can cross out answers A and C because they put 1 and 2 as the strongest, as the weaker acids. So between B and D, which one is a weaker or stronger acid? Is it 3 or 4? Well, if you compare 3 and 4, okay, and if you think about their conjugate bases, right? Let's imagine 3 was to lose its acidic proton. Well, what would you be left over with then? Well, you'd have this amine. And if this one was to lose its proton, if it behaved as an acid, donated a proton, we'd be left over with this amine. Well, you notice that in 4, that conjugate base is stabilized by the inductive effect of the chlorine, right? Which reins in that lone pair on the nitrogen and stabilizes it. And so since it's going to be a weaker base, it's going to give you a stronger acid. And so therefore, 4 is a stronger acid than 3. And so we see that the answer has to be D. Sorry, I was looking at something else here, but 4 is stronger than 3. Therefore, D has to be the answer. Now, if you look at B, we know again that this isn't the answer because 3 is weaker than 4 as an acid. But if we just think about 1 and 2, which one of these is going to be a stronger acid? Well, it's telling us that 1 is a stronger acid than 2. But if you think about the conjugate base that results if this was to lose a proton, right, you'd end up with acetone, which has a pKa that's equal to 19. And if this was to lose a proton, I'm kind of running out of space here, but you'd end up with isopropanol, which has a pK of like 17 or something like that. And so since acetone is going to be a stronger base, so to speak, since it has a higher pKa, then it would produce the stronger conjugate acid. So that's a way you could think about that. All right, moving on to question 16. Assuming equimolar quantities of reactants, which compound will react to the greatest extent with boron trifluoride in a Lewis acid-base reaction and why? And so first thing you should recognize is that boron trifluoride is a Lewis acid, right? It's an electron acceptor. And so we're looking for an electron donor. And if you look at all 4 of the answers, right, they all have electrons on nitrogen and oxygen. Well, we know that that answers A and C. Right away, we know that an amine is going to be a better Lewis base than an ether, is what we're seeing in C and D. Why? Because oxygen is more electronegative, so it pulls the electrons in more. Nitrogen is less electronegative, and so it doesn't pull the electrons in as much. And so the answer has to be either A or C. And as I just explained, it's not based off of atomic size, it's based off of electronegativity. And so the answer is going to be A. All right, number 17. Which one of these has the highest pKa value? So you remember earlier I said lower pKa is going to be a stronger acid. Therefore, we can say higher pKa is going to be weakest acid. And so we're looking for the weakest acid here. So you notice that they put all of the halo acids, right? I'll put them in order. We've got HCF, then we go down to HCl, then we go down to HBr and HI. Well, hopefully you remember that as you go down the group of the halo acids that they actually get stronger. So stronger. And in fact, HCl, HBr, and HI, these are all considered to be strong acids. Strong acids. Whereas HF is not considered to be a strong acid. It's actually a weak acid. And so it's going to be the answer. So I recommend that you memorize that. The HF is not a strong acid. It's a dangerous acid, that's for sure, but it's not a strong acid. Okay, rank these from from weakest to strongest acid. You notice that they gave us acetic acid. So acetic acid, as we said before, has a pKa of around 5. Then they gave us methanol, which is an alcohol. I'll just put, 17, something like that is good enough, okay? And then we have an amine, okay, CH3NH2. And if you're like, yeah, but you didn't give me the pKa of this compound exactly. No, I didn't before, but it did give you the pKa of an amine of ammonia, and we said that was around 38. So as long as we say this is in the neighborhood of 38, that's good enough. And so we see that the weakest one, right? The weakest is going to be the amine, right? And the strongest is going to be the acetic acid. And so the answer is going to be D. All right. Now, even if you didn't have the pKa's memorized, and I know I spent a lot of time in this video promoting understanding pKa's, well, if you studied from David Klein's textbook and you've seen the Aereo method of predicting acidity, you could use that as well. And you could say, well, in acetic acid and methanol, my acidic proton is attached to an oxygen, which is more electronegative than the nitrogen. Therefore, these ones are going to be stronger. So therefore, this is going to be the weakest. Okay. Then, if you compare the conjugate base of acetic acid, which would be an acetate ion, versus the conjugate base of methanol, which would just be methoxide, well, you've already done atoms, so then you'd go to resonance, and you see that we have resonance here. And so the acetic acid is going to be stronger because the negative charge is stabilized by resonance. Okay, let's take a look at question number 19. Which indicated hydrogen atom is the most acidic? This is where it helps to know your pKa's. And we have benzene, and I know we didn't go over the pK of benzene, but we know that this is an sp2 hybridized carbon that this hydrogen is attached to. So we'll just say maybe around 44, something like that. Then we have a hydrogen that's attached to an sp3 hybridized carbon, but that's adjacent to an aromatic ring, which is electron withdrawing. So we'll just say less than 50 for sure. Then we go over to C. And if you remember C, we have that 1, 3, right? 1, 2, 3. Maybe I should have numbered it like this. 1, 2, 3. The 1, 3 dicarbonyl. So by memorization, you would know that C has a pKa that was around 9, is what we said. I'll just put the number in there, around 9. And then this one here is next to a carbonyl, so it's going to be close to a ketone, which is around 19. So just like that, by memorizing some pKa values, you're done. C is the answer. You just move on with your life, okay? Now, you could probably try to solve this using Aereo as well. But again, I strongly recommend that you memorize pKa's in organic chemistry. I'd say it's imperative. Okay, number 20. What reason best explains why the K is greater than 1 for this reaction? So you should remember from your general chemistry days that K equilibrium is going to be equal to the concentration of products over reactants, right? I won't go over the whole thing right now. And so if the K is greater than 1, that means that the reaction lies to the side of the products. Okay, there's more products than there are reactants. Now, if we just take a look at what's going on here, you see that the methyl carbanion here is abstracting a proton from the 2-butyne, and then we end up with this carbanion here, and then we end up with methane. And so if we were to label our acid, we would say this is our acid, this is our base, we would say this is our conjugate base, and this is our conjugate acid. Now you notice that the negative charge in both of these bases is on a carbon, right? They're both on a carbon. And so if we take a look here, it says the answers are the conjugate base of 2-butyne. So they're all about the conjugate base of 2-butyne. And you should know that the equilibrium is always going to lie to the side of the weaker base, okay? So if we examine these two bases, which one of these is a weaker base? Well, the answer is this one is going to be the weaker base. Now, why is that a weaker base? If you're like the negative charge is on a carbon in both of them. Yeah, but in this one, right, the negative charge is resonance stabilized. Okay, that negative charge is delocalized, and so it's going to be a weaker base. And so we fleshed this out already, that the reason that the K is greater than 1 is because the conjugate base of 2-butyne, which is in the green circle, is a weaker base due to resonance. All right, number 21. Which statement is true? And you can see here compound 1 is a stronger acid, compound 2 is a stronger acid, and why? Well, right away, just by knowing your pKa values that I went over, you say this is a carboxylic acid, pKa is going to be around 5. This is an alcohol, the pKa is going to be 17. Even if you're off by a log unit, it doesn't matter. If there's a big difference between 5 and 17, 10 to the power of 12. So we know that this is definitely the stronger acid. And so you know right away that the answer has to be either A or C just by looking at it really quickly. And you see in A, it says compound 1 is a stronger acid because the conjugate base is resonance stabilized. Or in C, compound 1 is a stronger acid because the OH bond is shorter. Well, it's got nothing to do with bond length, does it? It's because, as I stated in a previous question, if you draw the conjugate base of that carboxylic acid, right, it's resonance stabilized. You can draw a resonance form here where that lone pair is delocalized. So we end up with something that looks like this. Those are the resonance forms, okay? So the answer is going to be this, whereas if I draw the conjugate base of this alcohol, which is going to be this, there's no resonance form I can draw for it, okay? There's no resonance form, and so the answer is going to be A. Number 22, again, memorize your pKa's, my friends. Rank these from least to most acidic. Let's go through them. Just by memorization, you remember that if we have an alkene, so if we have a bond between an sp2 hybridized carbon and a hydrogen, that the pKa was around 44. So I'll just put next to 1, I'll put close to 44. Here we have an alkyne, so this is going to be close to 25. And then this one here is an alkane, so we're going to say close to 50, right? There you go. So right away, you know, we're able to see just based off of pKa values that 3 is the most acidic, 2 is the least acidic, and so the answer is going to be C. Now, you could also do this based off of hybridization. You could say in 1, the carbon is sp2, and in 3, the carbon is sp, and in 2, the carbon is, in 3, the carbon is sp, and in 2, the carbon is sp3. So you could use hybridization as well. But again, memorizing pKa's is pretty great. All right, again, smallest pKa value. So if we take a look at A in question 23, we have an sp2 hybridized carbon. We'll just put close to 44. Then here we're going to put less than 50 because it's on an sp3 hybridized carbon, but it's attached to an aromatic ring, which is electron withdrawing. Here, same thing, we're going to put close to 44. It's on an sp2 hybridized carbon. And then in D, We're on an sp hybridized carbon, so 25. So even if you were off in your first three numbers, even if these were off by 10, you still see that this one is far and away the most acidic, right? It's much more acidic than all the rest, okay? And so there we go. The answer is going to be D. Number 24, it says, why is this first one, which is an enamine, okay, this is an enamine, okay, is a weaker base than number two, which is just flat out amine, like this, okay? And, it says here because the nitrogen in one, and I'm going straight for the answer here. I guess I'm getting a little bit tired, but it says because the nitrogen atom in one is sp2 hybridized, while the nitrogen atom in two is sp3 hybridized. Well, that's true. You can look at the hybridization here and say this is sp2, this is sp3, and since sp2 is smaller than sp3, right, then the lone pair is going to be closer to the nucleus, and therefore it's going to be a weaker base. Okay, it certainly doesn't have anything to do with steric hindrance. It's not really based off of stability because they're both stable, and because molecule 2 has more R groups, it's got nothing to do with that. R groups actually donate electron density based off of hyperconjugation, so, and it doesn't have more R groups on it. Okay, number 25, which carboxylate is the strongest base? Now, as you know, a base, if we think of the Lewis definition of a base, it's an electron donor. So if you look at all of these negative charges, which one of these is most willing to donate its electrons? What's the difference between these? It's the chlorines, right? If we look at this first one, it's got one chlorine that's pulling electron density away. In B, there's no chlorines. Here we've got one chlorine pulling electron density away. And here we've got two pulling electron density away. What happens when you're pulling electron density away, right, is that you're stabilizing, you're pulling in that negative charge and you're stabilizing it, making it less able to donate electrons. And so the only one that doesn't have that stabilization is going to be the strongest base, right? You could also draw the conjugate acid of each one of these, and you could say, well, A and C and D are all going to be stronger acids, they're conjugates anyway, are going to be stronger acids than B because of the inductive effect of the chlorine. So either way, you're going to end up with the right answer. Number 26, what is the weaker base and correct value for the equilibrium constant K? So let's take a look here. We've got a base here. So 1 is going to be our base, right? And so it's going to be abstracting this proton. I'm just kind of fleshing out what the mechanism is here. So we're pulling off this proton. And then, so this is going to be our acid, right? This is our conjugate acid. And this is our conjugate base. Okay, so that's what's going on here. And so if we look at the two bases, okay, because you see the answers all have something to do with the base. And remember, I said the equilibrium is going to lie to the side of the weaker base. Well, if we compare these two bases, you see that here we have the lone pair on this carbon, here we have the lone pair on this carbon, and both of these bases have a chlorine on them, which has an inductive effect. But you notice that in 4, that the chlorine is right next to the carbon with the negative charge, whereas in 1, the chlorine is 2 carbons away from the carbon with the negative charge. Therefore, this is going to be the more stable base, right? And if it's more stable, it's going to be weaker, right? And I said the equilibrium is going to lie to the side of the weaker base. And so the answer is going to be D. The K is going to be greater than 1, right? The equilibrium is going to lie to the side of the weaker base, okay? And it's because 4 is the weaker base because of the inductive effect of that chlorine. Question number 27, which carboxylic acid has the highest pKa? So if we're looking for highest pKa, we're looking for what? The weakest. We're looking for the weakest acid. And you notice that each one of these has an electron withdrawing group. Here we've got a bromine, here we've got a bromine, Here we've got a chlorine, and here we've got a chlorine. Well, which one of these has a greater inductive effect? Is it going to be the bromine or the chlorine? Well, chlorine is more electronegative than bromine, right? Because you remember the halogens come in the order fluorine, chlorine, bromine, and iodine, and electronegativity increases going up. And so if we're looking for the weakest acid, well, the bromine has less of an electron withdrawing effect, so that narrows it down to A or C. We can cross off these two. But then if we look at the proximity, well, you can see that in C, the bromine is further away from the acidic proton, right? This is the acidic proton here. And so C is going to be the weakest acid, and therefore it's going to have the highest pKa. Number 28, I like a little mechanistic question here. So what are the products of the acid-base reaction based on the arrows that are drawn? So we've got methoxide, right? And the methoxide is going to abstract the proton from the phenol. Then they're showing a pi bond being formed here. And then we're going to have a lone pair over here. And so if you look at B is pretty close, right? We've got our pi bond, but it's missing the lone pair here, okay? If you look at D, what's wrong with D? I see a big problem with D, right? This carbon has 5 bonds to it, so that's certainly wrong. I don't even know what the heck is going on in C. I'm very confused by that. But anyhow, they didn't draw the lone pairs here, but you can see the A is going to be the correct answer. Number 29, I guess I should highlight this. There we go. Number 29, what is the best description of the role of a curved arrow in a reaction mechanism? Well, if we just go to the question above, okay, what does a curved arrow represent? Right? A curved arrow represents the flow of 2 electrons, okay? So it shows the movement of bonds and charges. It shows the movement of lone pairs and electrons. It represents the flow of electrons from electrophile to nucleophile. It represents the flow of electrons from nucleophile to electrophile. Well, we're talking about mechanisms here, so we're not talking about resonance structures, okay? And so it's going to represent the flow of electrons from a nucleophile to an electrophile, because that's how electrons are going to flow. All right. Let's take a look at the last one here. It says, what are the products of the acid-base reaction based on the curved arrows here? And so to figure this one out, I just decided to redraw it, okay? Because they kind of drew the products in different orientation than they are in the starting material. And I thought if I drew them, and just kind of circled them, it might make things a little bit more manageable. So we have our starting material here, which is this cyclic ether, and we've got the acidic proton here. Then we have our sodium hydride. I'm just going to draw the hydride in for now. And so what's happening here? Okay, so we've got the hydride is going to abstract this proton, okay? Then we're going to form a pi bond here, right? We're forming a pi bond here. We're breaking this bond, and we're forming a pi bond here. And then, well, there's already 2 lone pairs on here, but then we're going to put another lone pair on here. So we're going to end up with a negative charge on our oxygen. And you see that in each one of the answers, okay? Now, let's see if we can draw it in the orientation that it's shown here. Well, the first thing that I notice is bonds that are broken, okay? You notice that you're breaking this bond because the tail of the arrow starts between this carbon and this carbon. So we're breaking that bond. And then I also notice that we're breaking this bond as well, okay? So when we break that bond on the bottom, the one that's highlighted in yellow, I'll highlight this one in green, okay? Then what's left over? If we're breaking the bond in yellow and the bond in green, you can see that we're going to be left over with propylene, okay? So this is propylene. And so right away you can see that B must be the answer because it's the only one that has propylene in it. But let's finish this out. And then if we look at this part, right, we can see that this part here went to make the propylene, okay? Well, what about this, all of this piece here? Okay, we have the oxygen and then we have 2 carbons. What's that going to look like? Well, it's going to look like this. You've got the oxygen with a negative charge on it, right? And then you've got this pi bond that was formed here. And so here we go. That's that there. And so you can see that this is the part I had in green. This is the part that I had in blue. And of course, when the hydrogen abstracts of hydrogen, then we also end up with hydrogen gas, right? Is formed. Okay. And so there you go. You can see that the answer must be B. All right. I hope you found this video helpful. And as I stated, one of the best things you can do is memorize some pKa values. I know I kind of snuck that in here as kind of like a little lesson on pKa values, but it's something that I learned a long time ago studying organic chemistry. The more pKa values and again, I don't like to use the E word in an organic chemistry video, but I'd say the easier the subject becomes. Yeah, the easier the subject becomes, the more pKa values you know. So I encourage you to start with this table and memorize those at a minimum. And if you have a great memory, try to memorize even more. And all right, have a nice day.